Dear colleagues, welcome to this webinar. This webinar is broadcast to you by Rock Science. The webinar title is Analyzing Reinforced Concrete Board Piles with RSPile. My name is Ahmed Mufty. I hold a PhD in geotechnical engineering. I'm a professional engineer in Ontario, Canada. And I'm a senior geomechanics specialist in rock science, responsible for the development of RSPile. Rock Science is a world leader in developing innovative two-dimensional and three-dimensional software for civil, mining, and geotechnical engineers. We are dedicated to deliver industry-leading software programs, exceptional customer service, and unparalleled technical expertise that engineers can rely on. From a team of about 4 people in the beginning, 25 years ago, the company grew to a team of more than 80 people with 4 offices and representatives across the globe. And we have more than 10,000 customers around the world. Our main office is in Toronto, Canada. We have another office in Vancouver, Canada, another office in Lima, Peru, and in Accra, Ghana. And the other office is in Gold Coast, Australia. And we have representatives all around the world. You can check these in our website. You can contact any of these if you're close to. We have comprehensive rock and soil two-dimensional, three-dimensional programs. The total number of programs now is 19 programs. We have a very active and interactive customer service and tech support. And we are obliged to, we dedicated ourselves to give innovative geotechnical tools and software to be used in everyday life of a geotechnical or rock engineer. Our programs, you can see these are the icons of the programs. So we have programs for slope stability, that is slide 2 and slide 3 for 2 and 3 dimensional problems. We have RS2 and RS3. These are finite element programs for general purpose excavation, stress analysis. You can analyze any kind of geotechnical problem with it. Seepage, you can analyze. You can use many constitutive relations. Examine 3, we have elastic, three-dimensional finite element analysis. I think there is boundary element also in it. Settle 3 is for settlement. RS log, you can use it for producing borehole logs and site investigation reports. There are other programs for rock analysis, slopes and rock fall and dips. And we have RS data for constitutive relations and interpretation of test data, and RSPile. This is the program we're going to talk about today. We have a very effective interaction between the programs and a general way of dealing and using these programs. So if you learn one of them, you can easily learn the others, how to use, because the way the icons, the way the flow of the program, most of the steps look similar. So you can see between these programs, among these programs, RSPile is having an interaction with the slide 2 and slide 3. So if you have a slope stability problem, you can use RSPile in interactive way with slide 2 and slide 3 of course, it is used as providing supports to the slope, piles supporting the slope. And you can see other programs, how they interact with each other. Let's go to RSPile and see what does this software do. RSPile is a program or a software made of 3 programs. The programs are capacity of individual piles. So this is the first mode in the program. We have pile groups analysis for pile cap and piles under a pile cap. And we have single or multiple piles analysis. This is what we are going to talk about today. And it is related to reinforced concrete also. So we are in the reinforced concrete mode. Now, in the last couple of years, we added the structural design part to the program. It's not a full mode, but it's a supplementary tool that you can use to design your reinforced concrete pile. The individual pile capacity is divided into 3 modes: driven piles, board piles, and recently, like maybe 1 or 2 years now, zoning and pile capacity table generator. The driven piles built in the program is closed pipes, open pipes, concrete piles, square section, timber piles, straight or tapered, steel ruled sections, and Raymond piles where there is a straight part and a tapered part at the bottom. In the plan, we have also helical piles. Hopefully this year we can accomplish that one. We have also the board piles. The board piles capacity calculations constitutes of rectangular barrettes, circular piles, and if there is an enlarged base, so circular piles with a bell or an enlarged base. The last part is zoning and pile capacity table generator. This is related to board piles because usually if you have driven piles, you will not have many choices and many depths. So usually you are having one type of pile and you know what's the capacity for a certain length or couple of lengths, and you distribute in the site based on that one. But for board piles, you need to study the diameter, the length, and the concrete capacity. So you need a table based on zones of the project. If the project is big, so you can divide your project into zones, and you can use cut-off levels and pile diameters and different lengths in each zone differently based on the boreholes and the soil layers of that zone. It's a very powerful tool. You can apply your factors of safety, your 3 types of factor of safety you can apply to this pile capacity table generator. The individual pile analysis, the second mode of the software, is made of behavior under load. So if you have loads and you want the response of the pile to these loads, and this is done for axial loading, for lateral loading, and for general loading, which is axial lateral. I advise that anybody is using RSPile for pile analysis to switch to general. It will help him always to change directions, to add more loads. Axial and lateral, it's specifically very important and very good for pushover analysis. We will talk about that later. But you can also use them for pile response to axial loads and pile response to lateral loads. In fact, we have now, you can import LPile data files. So if you have a file in RSPile, you can import it to RSPile through this analysis, through the lateral analysis. In the general loading, we have the pile response to general loads, axial loads. Of course, we give the loads in global directions. So vertical loads, horizontal loads, bending moments, couples are on the head of the pile. You can apply tractions along the pile length, and also you can apply a load in any direction and at any point. So if you have a horizontal point like 3 meters below the pile head, you can apply that one. If you have a no-cell test, you have a load on the pile from the bottom, you can apply that one. This makes this program specifically designed for the needs of a piling engineer. Now, coming very soon, like in 1 or 2 weeks, we are adding this feature, which is the head loading, multiple load cases. So this is useful for structural and piling engineers that are interacting with each other. And the structural engineers may use this program to have the response of the piles to the loads generated from the superstructure. And you can analyze as many piles you want, as many load cases you want. So you may have 1,000 piles in a project and 1,000 load cases. This will help you to run all the load cases, which is 1,000 by 1,000, 1 million load cases. You can run them in one shot. We have in the individual pile analysis what is called the pushover analysis. The pushover analysis is very good to estimate the load settlement or load displacement curves of the piles. Before you start the test, you expect something, and you can calibrate your soil parameters after the test to simulate the test with the same curve generated from pushover analysis. Length analysis we have. So if the pile, you don't know at which length will behave better for you, you can have a sensitivity analysis in length. We have also behavior under soil displacement. So you can have the soil is moving, and the movement of the soil will affect on the pile. So you can have a displacement profile applied to the pile, or you have a sliding displacement, like a block of the soil above a certain point, above a specific depth, will start moving towards the slope inclination. And this one is integrated with the slide 2 perfectly. So you can put an RSPile in slide 2 as a support, and you can have a full analysis of RSPile without using RSPile yourself. The program will go to RSPile, automatically run everything, get the results, and come back and add the shear values that produced by RSPile at the location of the slip surface to get a factor of safety for the slide. We have also, we can produce for you the QZ, TZ, PY curves. So the interface curves between the soil and the pile can be reproduced and generated over the length of the pile. We can also make a pile stiffness analysis. So sometimes the structural engineer needs to have the 5x5 matrix, stiffness matrix, to be added to the node at the reaction. So he can get this from RSPile very easily. The mode analysis of pile groups, we have the cap, design of cap, and the piles, type of piles, connectivity, orientation and elevation, and group effects. We have also the loading can be general loads, and also group effects from the soil PY curves or TZ curves, you can apply your multipliers. Now in the structural option, this is specifically useful for board piles, which we are going to talk about today. We have two major parts that you need as a pile or structural engineer. That is the interaction diagrams and the capacity ratio. Interaction diagrams, we have different concrete stress-strain relations to construct the interaction diagrams for you. So starting with modified Hognestad, this is a very, very popular stress-strain curve and acceptable by many codes. Specific ACI 318, 19, and 22, they are the same. Whitney block, stress-strain curve. Now we are adding Eurocode 2, the three models of Eurocode 2. So we have additional three stress-strain curves, and we are adding also the Canadian Standard Association A23.3, the stress-strain relation, which is also a block. We can add different material factors. So you can have a single factor on the interaction diagram. Or for today, you have ACI 318 factors. Of course, Eurocode doesn't have factors. It's already factored. The 3D view we have, you can use a 3D surface and look at it from all aspects to see how your interaction diagram is rotating around the force axis. And this 3D surface is used to get the capacity ratio. So the capacity ratio in our software is the demand divided by the capacity. So if the demand biaxial moment capacity exceeds the biaxial, if the biaxial moment applied exceeds the biaxial moment capacity, you will have inadequate section. And the same for the axial load capacity. If your axial load exceeds the axial load capacity, allowed, of course, because you need to calculate some maybe factored axial load capacity, the same indication you will get that the section is inadequate. The theoretical basis of RSPile, for the vertical analysis, we have for the axial analysis, we have the TZ curves, which represents the soil spring models for the side of the pile. So from this we get the skin friction, and we have the base spring model that is called the QZ curves, and we solve this equation. These curves, whether the TZ, whether the QZ, are built in RSPile. So you can choose any of these, which are well known in a couple of standards, including, for example, FHWA, maybe other AASHTO maybe, and you can also apply elastic soil. So it should be coinciding with previous elastic methods. Or you can have a user-defined stress-strain curves or TZ curves and QZ curves. You can get them from the site, from a preliminary test or on an OCL test or whatever. For the PY curves, which is for the lateral analysis, we have to model the soil for the lateral analysis. And of course, at each depth, you may have different PY curves. So there is some displacement, and that displacement will lead you to curves like these, which are called the PY curves for different soils. For example, this is for clay with free water. This is for soft clay. This is for drilled sand, for API sand, like that. Weak rock. So it starts with some information you need to input, which is, for example, initial stiffness and the strain 50% value, things like that, then you can apply the name. You can also use elastic, and you can use also user-defined PY curves. The bending stiffness is well known for everybody. You're all familiar with this. EI equals M over phi. Phi is the curvature, and M is the bending moment. Now, if the section is not reinforced concrete, this is simple, because EI will be, let's say you have elastic section, so EI will be constant. And if you have a plastic section, after the bending moment reaches the plastic bending moment, the relation will be easily found. But for reinforced concrete, we will see how this is changing. Due to cracking in concrete, you will have changing bending stiffness with the level of load you are applying. Now we are let's start with the structural design. So to start with the structural design, you need to define your sections in RSPile. So you have 4 types of sections in RSPile. You have elastic section, you have plastic section. Sorry for this one, it's mistyped here. It's plastic section. No, sorry, it is elastic plastic, correct, it's the same. Elastic plastic section. So starts with an elastic part, then after it reaches a limit, starts to be plastic. And we have the reinforced concrete, which we are going to talk about today, and the pre-stressed concrete. The reinforced concrete will be controlled by interaction diagrams and capacity ratio for the design purpose. Of course, sections like elastic will not fail. Plastic will fail when you reach the plastic moment. Pre-stressed concrete, you can check the failure of a pre-stressed concrete by the divergence of the analysis in the program. So as long as you're not diverging, the pre-stressed concrete is working fine. And you can check the stresses later. We are dealing with today with the reinforced concrete sections. We have 2 types of reinforced concrete sections. We have circular sections and rectangular sections. Now, after you define your sections, you need to define your pile type. What is a pile type? If you are familiar, you are all familiar, in fact, with a pile design. So a pile design, you may have different reinforcement through the depth. You may have different section diameter, for example, or section dimensions with the depth. Maybe you have enlarged bays at the bottom. So the pile type defines the pile's segments for you. For example, this segment, you have a permanent casing. The bottom segment, there's no casing. So you can define your pile type in this way. So after you define your pile types, you can choose the pile type you want for the pile number specifically you are, or let's say, in question. You can see here, for example, this is a real pile, one of my old designs. So we have here 2 parts. The top part is reinforced differently than the bottom part. The top part is reinforced by 14 32 millimeters bars times 2. So you can see the section here. And the bottom part, which is A2, is reinforced with 25 millimeters bars. Let's look to this in a demonstration. You can see here I defined the 2 soil layers. I gave their, of course, you go one by one. So you go to home, you go to project settings, you choose general, you choose your units, then you go to, you choose pile analysis, then you go to pile analysis type, and you choose whether you want actually loaded or general or lateral. So if you're using axially loaded here, it doesn't matter. We're not running. I'm just showing how the sections are defined. So if we click right on this pile, we can see the pile is defined by its number, by its name. You can keep the number shown like this one. You can see here, pile 1. And you can remove the number by going to view, here to view, and to change the display settings. Now, here you can see you are choosing the pile type. So in this model, we have only one pile type, and I chose it here. So let's go and see how this pile type is done. First, we go to sections. You can click right, and you can go to pile section properties, or you go to piles and pile sections, and start defining your reinforced concrete sections. So here you can see I'm defining 2 sections, A1 and A2. I'm choosing reinforced concrete among the 4 types I talked about. I'm putting the cylinder strength of the concrete, and I'm choosing circular, not rectangular. If I choose rectangular, I will have 2 dimensions. If I choose circular, I have 1 diameter. Then after I choose the diameter, of course, I can change to millimeters here. Or if it is in US customary units, you can change between feet and inches. You go to design after that. If you go to design, this dialog box will appear for you. And you need to put your patterns of reinforcement. So in the beginning, there is nothing here. And this is all empty. What you do, you press the plus and you get pattern 1, and you choose your reinforcement from here. I chose Europe BS 4449 32 mm. So 32 millimeters bars. And I chose the distribution of the bars radial. So it is all around. We have another one which is rectangular. So the bars will be in rows and columns. And there is custom also. Custom means that you need to put your bar X and Y, X prime, Y prime, local coordinates of the section. In X prime, Y prime, from the center for each bar. Why this is important? This is important in reanalyzing piles. So if you have a pile and your bars are shifted, 1 bar is missing, 1 bar fall down, you can't catch it anymore. So you need to analyze a section based on not a systematic distribution of bars. You can put any bars in anywhere you want through the custom. Again, then you will have here the reinforcement ratio, the pattern reinforcement ratio, and the total reinforcement ratio. Why we do patterns? Why don't we have 1 pattern? Because every pattern may be different. For example, this one is 32 millimeters, and the other pattern is 25 millimeters. So you have 1 bundle of 32 and a bundle of, and the other bar in the bundle is 25. Although, if you have bundles of the same bar, you can use bundled bars here. You can check this and change the number of the bars in a bundle. Here you add the yield stress and the yield strength and the elastic modulus of the bars. You can add casings to the section. You can add a core to the section. You can, after lining the core, you can fill the core here. You can add an I-beam to the section. You can choose anyone from the Canadian or the American, built in. Now, after you finish this one, you press OK. You will get the design of A1. The same thing you do for A2. Pile sections, A2, reinforced concrete, concrete strength, circular 1 meter diameter, and design. Here you can see we have one pattern and the bars are 25 millimeters now. Of course, you can decide your cover. This cover is from the edge of the pile to the edge of the bar. To the edge of the bar, not to the edge of the spiral reinforcement. Okay. We continue. This is the pile types now. So you can build up your pile with pile types. Let's see the analysis. So this one you can see, when you choose pile types, you name the pile type. You have orientation, so you can give inclination and rotation to the pile. You can enlarge the bottom part. The bottom part you can enlarge with a bell, and you can give lengths for each segment or coordinates for each segment. And you can design the bell with its dimensions. You can define by coordinates, or you can define as here written by segment lengths. So if you uncheck this one will appear for you to change. You can delete and add sections as you want. And it's good you can have copy, so you can copy the pile types to many names. Then you change the things that are needing changes only. One of the major benefits of using RSPile is that we update your bending stiffness in reinforced concrete during the finite element solution iterations. So if you see, depending on the bending moment, you have a different bending stiffness, changing bending stiffness with bending moment in reinforced concrete sections. And also depends on how much is the axial load. So if you have a higher axial load, you will see a different graph. If you have less axial load, you will see different graph. So we have a gross moment of inertia for a certain rotation. After that rotation of the section starts cracking. So it starts progressive cracking, and at this point, reinforcement starts yielding. So the shape of the bending stiffness, bending moment graph will take another shape. We update this shape during the analysis. That's a very important feature in RSPile. So you can have different M5 values at different depths. It's not single for the whole pile from top to bottom, because usually before or other programs you may see only one relation between M and phi. But in RSPile you can be sure that your M phi is getting updated. Let's see a demonstration of a pile under lateral analysis and how we get the results of the section, of each section. So you can see here, this is the pile, and I have 4 boreholes, and I added one pile also on the borehole, exactly on the borehole, for you to see how this affects the results. So I have an offshore pile covered with water for some depth, then the soil starts. And I have 4 boreholes, and I have the following conditions. I have a permanent casing at the top part. After the permanent casing, I have 1 meter continuing with the same reinforcement. Then the reinforcement is decreased to half after that one. So I have 3 parts of the pile. And I have a deck here, which is not allowing the rotation of the top part. And I have a traction force from the wave action laterally applied to the pile. And I have two horizontal forces here, 25, 25. In fact, it's 50, but I divided it to 25, 25. It doesn't matter as long as this part is not rotating. So wherever you put the point, the forces, you will get the same results. Now the first section at the top is this one, having two patterns of 25 millimeters. The second section is without casing and having two patterns of 25 millimeters. And the third one is the bottom part has only one of these patterns, and the second pattern disappears, and there's no casing. And these are the lengths 9, 1, 10. So total length of the pile is 20 meters. And you can see here the boreholes and the location of the pile, and that's how it is modeled in this one. The same pile is applied here also to see the difference in the deflection and the difference in results, because this pile is at this borehole. Why? Because this borehole, if you see, the soil is higher. When the soil is higher, displacement will get less, moments will get less. That's the use of RSPile. RSPile is very important for people who want to have more than one borehole in the analysis. Usually, piling software, they have a single soil layering system, so one borehole. But in RSPile, you can have in the same project, different piles will have different behavior because of different boreholes. You can also have very nice looks for the boreholes, like this one. See, it's beautiful, right? Without the lines. I like it. Now the analysis results. Let's see the loads, how they are applied. So we can go to adequacy. In adequacy, you have loading. So we added the 25 kilonewtons at the top. One is 0 from head. The other one is 1 meter below the head. And we have rotational stiffnesses. I added rotational stiffnesses, very high rotational stiffnesses at 0 and 1 meter depth, so that it will act like restrained from rotation. Of course, you can add another way. You can add a slope 0 here, this one. You can add a slope 0. You can put a slope and give a 0 to the depth you want. That's also possible. This is the loading I told you about. You can always choose general is better than using X and Y. So you have more flexibility in adding and changing directions of load. But if you have only you are importing RSPile, or you have only axial analysis, or you have only lateral analysis, it's fine. You can keep it as lateral analysis. Tractions. So the one we have just seen here, we have from 6 to 4 and from 4 to 3. Although it is curved, but I divided it into 2 segments because RSPile allows only for uniform tractions. So I took from 6 to 4.5, from elevation 3 to 0, which is 2 meters head, 2 meters from the head, and 5 meters from the head. And then the second part is from 4.5 to 3. And you can see it here again. So from 2 meters to 5, changing from 6 to 4, and changing from 4 to 3, from top depth 5 to 6.5. Now we can after applying the load, the soils, and everything, we can also see how the sections are designed. These are the sections. So you can see this is 1 meter with casing, section without casing, and section with less reinforcement. The same way, everyone has its own. Let's see this casing one so that you see how we can add a casing. So that's the casing. If you come to casing, you will see it checked, and you have thickness of the casing and yield the strength of the casing and the modulus of the casing. In project settings, in the analysis, you can go to something called interaction diagrams here. This interaction diagrams tab, you can keep it unchecked. It's fine. Or you can check it, and this will take a little bit more time to get into the interaction diagrams because it calculates a lot of points in that interaction surface. And here you choose the stress-strain relation, and here you choose the number of points in MX/MY curves and number of divisions for the angle to get PM curves. Now, if we run this one, we will get these results. So these are the interaction diagrams. You can change here which sections you want. So this is the biggest interaction diagram. The largest ones are for the casing part. So if I remove the casing part, I have section 2 and section 3, the section without casing and section with less reinforcement. And also I can see the 3-dimensional surface if I press this one. If I press this, I'll get this. See how it looks like? Very beautiful presentation of the interaction. So if you are asking where is the 12, these are the 12. See, 1, 2, 3. These are the 12 load levels to get the MX/MY curves. And the 32 graphs are these ones. 1, 2, 3, 4, like that, around 32 divisions for the angle. So the PM curves you will get here using the angle, and the MX/MY you will get through the levels of the load, axial load. You can change the transparency, and you can check other sections because you have 3 sections. You can see the other sections. The maximums will show here for each section. This is for the one with casing. It's bigger and it has some expansion at the moments level. The results of the program will show like this, because if you go here in the original program, you go to results and you press on RSPile, and you will get the results of this pile. Results will show like that. So you have displacement, shear, and we have something here called the capacity ratio. We can add capacity ratio to the results. So you can see the capacity ratio is here in the table. It's increasing to a certain level, then decreasing again, then increasing again. What happened? Increased again. Why increased again? Because the casing is finished. After the casing, the bending moment capacity decreased, so the applied moment divided by the bending moment capacity got a higher value. If this value exceeds 1, exceeds unity, the cells will turn immediately into red cells, indicating inadequacy of the section. If you have pile axial load tests or lateral load tests, and you want to graph these pile load tests before you get into the site and do the load test, or you have a load test and you want to calibrate the soil PY curves and TZ curves that you have. So you can go to something called the stiffness analysis. You remember this, the edit pile. You go to advanced tab. You check on stiffness matrix calculator. You check, so you press on settings. You put number of points, number of steps you want, and you put the load you want for the stiffness. The load, of course, will be the highest load you expect in the test, and you will get your results like this. You can see your results like this. The results will come into Excel sheet. You can have your Excel sheet here. You can press in the results. You will see Excel sheet. You can press on Excel sheet and get this one. And you have the pile head deflection. For example, if it is lateral analysis or axial analysis. So Z prime is for axial analysis. And you have the stiffness, axial divided by the displacement, axial load divided by displacement. If you multiply the deflection by the axial stiffness, you will get the load, this one. And I multiply the deflection by, it is settlement, in fact, this one. So I multiply the settlement by 1,000, I get millimeters. And I add 2 zeros at the top, I get the load settlement curve. The same thing I can do with pushover analysis. So you can see these are two piles. One is elastic and one is reinforced concrete, and they are the same piles for the other one, for the stiffness analysis. And we shall see how pushover is done. So in pushover, stiffness, they are the same method. So you go to the pile, you go to edit pile here, you go to advanced, and you press on pushover analysis. But pushover analysis, if it is axial, you need to choose the axial mode. You go to home, you go to project settings, you need to choose axial mode. If you are doing a pushover analysis in the lateral direction, you need to choose lateral load. It should be consistent with the project settings. Now, after I added these, you can see here, I added 37 millimeters as a maximum deflection with 37 steps. The same for the elastic. Where did I get this one? I got it from the stiffness analysis. So in fact, it's the load I am applying to the pile also. You can see in edit pile loading, it's this load. I'm applying it here to the pile, and I want for the same load how the load settlement curves behave, load settlement curve behavior is. So after that, I press on compute, and I get these results. So this is the axial head displacement and the axial force. You can see it is similar to that of the stiffness analysis. You can go to Excel sheet here, and you press on it on the Excel sheet, and you will get something like this. This is for the stiffness. So stiffness analysis, you can get something like that at the end. This is how I told you to do for millimeters and load. And here also millimeters and load coming from pushover analysis, which is this one. Oh, no, sorry, this is for the reinforced concrete. So this is reinforced concrete, and this is the elastic one, two piles. And you can see they are almost coinciding because the pile is rigid compared to the soil. So soil is the one giving the nonlinearity, not the pile. I gave the same elastic modulus of ACI, 4,730 times the square root of F sub C prime, as a modulus for the elastic pile. And I kept this as a reinforced concrete section. And I got almost the same result, because the pile is behaving as rigid because the soil is the weak part. So the nonlinearity of the behavior is coming from, in the load settlement curve, is coming from the soil, not the pile. Pile has only elastic shortening here. So in structural design, you need to remember that you have specific direction of load application. So you remember the right hand rule to apply the moments positive and negative, and the loads you apply are always in the global axis directions, not in the local, because you can rotate the pile in the local coordinates, but the global coordinates of the project will remain the same. So you can see here the moment around y, the moment around x. Just put your thumb in the direction of x prime or y prime. You can estimate what's the moment that you're getting from the analysis. RSPile interaction diagram covers all the cases of compression. So searches for the neutral axis and its inclination. And the same thing it does for the tension. So don't worry about whether you have tension or compression, they both work. And also fully tension, fully tensile load, or fully compressive load without moment. This is how the parameters work for the interaction diagram. And these are the interaction diagrams that we get usually. This is the PM curve I'm talking about. When you have a specific alpha, you can change the alpha. I can show you that. You can change alpha here. You can put any angle you want or any load you want here for this one, and you can get different interaction diagrams. It depends on the interaction diagrams results depend on many points, like the number of divisions, number of slices in the reinforced concrete, how much factors you're adding, and time will be greatly affected by these two factors, by these two numbers we're putting here, number of load divisions and number of angle divisions. These are the ACI load factors we apply in the program, and I showed you already how does that work. And the capacity ratio is the demand, so this it's the moment applied divided by the moment capacity at the level of the load we have, the ultimate load. So the factored interaction diagram. There is another way for getting the capacity ratio, depending on the diagonal direction of the moment axial load vector, but this one is not applied in RSPile for the time being. I already showed you how capacity ratio works, but I want to show you for another program, for another model, how the capacity ratio, when exceeds 1, the cells will turn into red here. So you know this part here, small part here of the pile, this segment is not adequate. So you need to increase the reinforcement or increase the diameter or change the material, increase the material strength.
No, thank you very much, Dr. Mufty, for this excellent presentation on RSPile and the demo of how you use that for reinforced board piles.
Thanks to all the attendees. Hopefully we will meet you again in another webinar.